Welcome back, everybody. So let's get going with the second part of this lecture.
So let's start with a question.
Exactly, yes.
So the Cartesian product is not commutative, therefore it's important that the order is right. But if I reorder the columns, would I still have a relational table?
So it's a very good question, because that actually will give me the transition to a second definition of the tables. Do I have it here? So basically, it is true that the Cartesian product is not commutative. Another way to explain that the Cartesian product is not commutative is that the order of the columns is important. It means if you have a domain like universities, cities, and dates, you must have the universities in the first column, the cities in the second column, and the dates in the third column. In other words, the index of the elements in the tuple is numbers, right? If you go back here, right, there is T1, T2, Tn. T1 is a university, T2 is a city, and so on. Commutative would basically mean that you could swap the order here. You could say, you know, instead of universities and cities, you could have cities here and universities here. But if you take this definition right here, this would be a different relational table. So if you swap the domains, that would still be a relational table, right? Because you would still have it as a Cartesian, as a subset of the Cartesian product over domains, right? It's a relation over domains. But it would be a different relational table. That's what's very important, right? The table in which you have universities and cities is not the same table as the table in which you have the cities and the universities, right? Did it answer your question? Awesome. And in fact, this is a problem. It's a big problem, because if you think of a relational table, the order of the columns should not matter, right? As long as you know where the universities are and where the cities are, why would it matter that you have the university on the left and the city on the right, or the city on the left and the university on the right? It's the same semantically. So that's actually a problem with the definition of a table, a relational table as a relation. So I'll come back to that in a few minutes. Okay. So let's go back to our example of tuple. So if we define a relational table as a relation over domains, in that case, it's a relation over universities and cities, then an element of that relation is a tuple, T, and T1 denotes the first element of the tuple, that would be T1, and that would be T2, right? T1, T2. T1 is ETH Zurich, T1, T2 is Singapore. These are mathematical variables, if you want. Okay, now you can generalize. So this was with 2 columns. You can have it with 3 columns, which means 3 domains. So here we have a domain D1, a domain D2, and a domain D3. So this is the domain D1, this is D2, this is D3. So if we define a relational table with these domains, we would say the relational table is a relation over D1, D2, and D3. Or equivalently, it's a subset of the Cartesian product D1 cross D2 cross D3, just repeating things a lot. An element of that relation T has 3 elements, T1 that belongs to domain D1, T2 that belongs to domain D2, and T3 that belongs to domain D3. So this was the first idea of, this is why it's called actually a relational database. This is why it's relation, right? It's a relation. So we have these numbers that helps indexing the columns. But in fact, in real life, I don't know if probably all of you already have spreadsheets, right, in Excel or OpenOffice or LibreOffice or whatever. I doubt highly that you call your columns with integers. You probably put headers more like that, right? Name, city, birthday, and so on. This is how people do it. So this is the first problem of the relation definition, because in the relation definition, we don't have these attributes here. We don't have any way of defining the headers. All we have is numbers, T1, T2, T3. So this is also a problem. The commutativity is also a problem. We would like it to commute, but sadly it doesn't if we define it as with the Cartesian product, right? All right. So here's again the example of universities, cities, but now I have proper headers. Instead of 1 and 2, I have university and city here. So that's my header. These are the names of my attributes, and this is the data. Okay. For this reason, I will give you a second definition, an alternate definition. Yes, there is a question. Maybe we can throw the catch box over there on the right.
So you said that a tuple is a row, right?
Yes.
Like horizontally. So
Yep.
intuitively, when you say T1, T2, T3, shouldn't it be like T1, T2, T3 instead of the column?
Ah, I see. I see. So indeed, T, that's a horizontal slice. That's a row. This is T1. This is T2. If you would designate another row, like for example here, I think you would probably call it U or V and so on, right? You would give it other letters. This is T, this is U, this is V. I think that this is done in database design theory. We'll see in a couple of weeks. So in fact, it's all a matter of convention, right? It's a mathematical convention. We just make the convention that if we put a subscript right here, we actually mean the individual values over the same row. You could, as a mathematician, you can do whatever you want with the math. You could also have said, we call this tuple T1, this second tuple T2, and this third tuple T3. We could have done that. It's really just a matter of convention of how we want to do it. And in database textbook, typically, the convention would be that the subscript here doesn't mean the number of a tuple, but it really means the element of the tuple that you want to get.
So we're going to maintain this throughout the course. When we say T1, we mean tuple T, element 1.
No, but that's because I'm moving to the second definition.
Ah, okay.
That's exactly the reason. So the reason, it's basically confusing. I agree it's confusing. And this is, I think it's an issue of the current database textbooks that use this sort of definition, right? We'll very soon see, I can actually already tell you now, instead of the number, what we will use is the name of the column. So we're going to say T university and T city. And then the problem goes away, right?
Thank you.
Thank you very much. That's a very good question. Okay. So I'm glad that you also have these issues, right? And in fact, I discussed with colleagues who are also teaching databases, especially in the bachelor's level in computer science. If you actually teach that a relational table is a relation over the domains in that way, a lot of the questions are not actually questions on the actual database thing, on the actual database theory. It's rather going to be a question on the limitations of the formalism. So this is the reason why I have this second definition for you that is coming right now. All right? So let's go back to what I said about the atoms of a table, the attributes and the values. So what are the attributes? This is an attribute. This is an attribute. An attribute is a string, right? University is a string. City is a string. It's just the name of the attribute. So an attribute A is a string. These are examples of attributes. So this is, you know, the foobar where it comes from? Who already heard foobar? Okay, it's a computer science thing. It's a geeky thing. So foobar actually comes from the German furchtbar. And somehow it started as a pun. And then whenever you want to give an example and you are too lazy to figure out a string, you just call the first string foo and the second one bar and the third one foobar. And this is how you get these examples in many computer science lectures with foo and bar all over the place. So this is why I have it here. But typically, this would be like more common attributes: the first name, the birth date, the product ID, an account ID. These would also be strings, but I doubt that you want them as attribute names, right? But for the purpose of our definition, we don't care. We just say an attribute is any string. You can call them whatever you want. In fact, if you call your attribute ETH Zurich, I'm pretty sure the system will not complain, right? The system doesn't know about English, right? Okay, so let's now, instead of defining first the relational table as a relation and then a record as a tuple in that relation, we'll do it the other way around. We'll first define a record and then we'll define the relational table. So remember these two ingredients I gave you at the start? The attributes, the values in these ingredients like cooking like. So I need two things. I need a global set of values. These are all the values that I can have in there. everything, the strings, the dates, the booleans, absolutely anything you can fancy. And I need a set of attribute names possible, but let's take the set of all strings. These are to be strings. What is a record? A record is a map, partial function, a map from strings to values. Remember that notation? It's a map with a little cross here. The cross means that you don't associate all strings with a value. You associate some strings with a value, right? So it's a map from some strings to values. So T is an element of the set of maps, right? Of strings to values. Now you understand why earlier there was this example, one of you was asking, why didn't you say strings to strings? That's because the way I have my second definition of a record is from strings to values. All right. Normally, you have all the math you need to understand that. However, if you have a visual, it actually helps. So this is the visual. This is an example of a map where I'm listing the mappings, right? And I use this notation with the little vertical bar on the left. And that means name is associated with Einstein. First name is associated with Albert. Physicist is associated with True. Year is associated with 1905. By the way, Einstein is right there outside. You can speak with him if you want. So we associate some strings. In fact, in that case, we only associate 4 strings with values. And these values here can be any value. This is a Boolean, this is a natural integer, these are strings and so on. This here is a record. It doesn't look like a record because I haven't drawn it yet like a table row, but this here is a record. It's a map from strings to values. This is just a slide of earlier when I explained what a map is. So you could also draw it like that. But it's easier to understand, especially for databases like this. There is, in fact, a syntax. So this is the same thing, right? This would be the mathematics way of putting it. This would be a textual way of putting it. Does anybody recognize this syntax? What is this? Yes? Yes, that would be a Python dictionary, absolutely. Do you know what Python dictionaries are syntactically? Yes? JSON, exactly. This is JSON, right? So in fact, JSON we'll see in Big Data for Engineers, not now, but here you can see that in fact, what we defined as a record from maps to strings is in fact a Python dictionary if you know what Python dictionaries are, and it is a flat JSON object. If you don't know what JSON is, don't worry, because this is how in this lecture we draw it. It's 3 times the same thing. This is the same as this, But as a relational table, we prefer to view it that way, where we have here the headers, which are strings, and here the values, which belongs to the set of values. So basically a record is 1 row, right? So this is just 1 row. This is my row, but I also put the names of the attributes here because we want to know what the values are. Now you see that addresses the question you asked earlier on Zoom. The order here is irrelevant. Why? Because in a map, there is no order here in the way we map things, right? There is no order at all. So we could swap the columns, left and right, that would still be the same record, right? So this is much better to define it. This here is an example of map. Now, university is ETH Zurich and city is Zurich. This is a map, mapping strings to values. And again, the order is irrelevant. If I swap and have the city first, the university next, that's fine too. Okay, so my headers, so the headers that corresponds to a specific map, let's call it H, it's a subset of the set of strings. So this here is a set of attributes. It's a set of 4 attributes, a set of 4 strings. We call the support of a record or the support of a map, it's the set of strings that are associated with something. So if I go back here, what is the support of this map here? It's these 3 elements. It's all the elements that have an arrow that starts from them. This here is not part of the support because it's not associated to anything. So the support of this record is the set of these 4 strings. The support of this record is the set of these 2 strings, and so on and so on, right? So the support of this here is the set of these 4 strings. The order doesn't matter. All right, now, if I define a record as a set of maps, and I want now to define a relational table, what can I do? I can pick records. Let's pick 1,000 records, and let's try to assemble them into a relational table. So I picked here 3 records, 3 maps of strings. They fit the definition, right? But do you see the problem here? I cannot assemble that into a table. Why? Why cannot not paste that together as a table? Yes? Exactly. There doesn't need to be a map for all of the attributes. So not all attributes are mapped in the same way. Another way of putting it is these 3 records do not have the same support. They don't have the same headers. These do. If you take these 3 records, 1, 2, 3, you can actually assemble that into a table like this, right? And then, since they have the same support, you don't need to repeat the headers. It's always the same. So you just put it once, as you would do in Excel, right? That these are your headers. And then you have here the records. In other words, a relational table is a set of maps that have the same support. That's a constraint, that they must have the same support. It's called relational integrity. If the set of maps is such that all maps have the same support, then you can nicely draw a table like this, and this is our relational table. So now, if you do the math, what do you need in order to define a relational table? It's made of a set of attributes right here and of an extension right there that is the set of maps. So you see that's the fancy thing. It's a subset of the set of maps. And it's such that for every tuple in my extension, the support of the tuple must be the exact set of attributes here. Now, you must have, it must itch a little bit because I use the word tuple. So here I'm being databasey by calling this a tuple. In fact, database people call it tuple or record or row or, or interchangeably. A mathematician would say, wait, that's not a tuple, that's a map, right? But again, in databases, when we talk casually about tables, we just still call it a tuple as a synonym for row and record, right? So this is why I called it T. Okay, but anyway, I have maps here, and all of the maps here have exactly the same support. They map exactly the same strings to values, and we have a nice table that looks like a big rectangle, basically. All right, here's another example where we have 3 attributes: customer ID, security ID, quantity. So my set of attributes in that table that I call holdings is customer ID, security ID, quantity. It's a subset of the set of strings. That's how I define my attributes. And now I add an extension, which is a set of maps in there. All these maps must have their supports matching exactly my set of attributes. Now, if I draw it mathematically, this is how a mathematician would say it, right? Customer ID is 1, secure ID is CH, plenty of zeros, quantity 135. That gives you your first record, or your first map, or your first row, or your first tuple, no matter what you call it, right? Okay, and so here, this is a map. This is another map. This is another map. This is another map. 1 map for every record, right? So this here must have the same support. And you see they have the same support. It's every time customer ID, security ID, quantity. So this matches the definition of a relational table. Now, we are coming back to the question you asked earlier about T1, T2. If we call T one of the records here, I still keep that letter T because we used to call it tuple. So if T is the map that maps customer ID to 1, security ID to this, and quantity to 135, then I'm going to use this convention with a dot, T dot customer ID equals 1, T dot security ID is this, and T dot quantity is 135. You can also use a subscript. You could also say T and then as a subscript customer ID, or T as a subscript security ID. Why do people like to use a dot? Because this is how you do it in Java, in Python, and so on, in JavaScript, right? In order to access a property of a tuple or a property of a dictionary. So this is the computer sciencey way of writing the subscript. But you see, what changed now is that we no longer say T1, T2, T3. We say T customer ID, T security ID, and T quantity. Okay, who is following? Awesome. Okay, so now what is a database? It's just a set of relational tables, right? I have, in that case, 4 relational tables. Of course, my relational tables will have different attributes, right? Different supports. That's totally fine. But within the same relational tables, all of the maps, all of the records must have exactly the same support. Okay. I think that's mistakenly here, but anyway. So now let's move on to the notion of schema of a relational table. So I have something that I haven't yet brought to my second definition. Is that in my first definition, we defined the domains. We said we have strings, we have booleans, we have integers, and then we defined the table as a relation over strings, boolean, integers. But in my second definition, I didn't have any domains. I just took the entire set of values and I just said, okay, it's just the maps from strings to values, and that's it. So there was no domains at all. So I have to bring them back in some other ways. And in fact, this is what schemas are for. So these extra constraints that we now enforce that within each column, it must be the same type of value, is called domain integrity, right? That's my second constraint. So I'm going to say, for example, customer ID must be an integer, security ID must be a string, quantity must be an integer. You might even ask it for it to be positive. So in other words, the domain of customer ID is n. The domain in my, that's the name of the relational table. The domain of holdings of security ID is strings, the set of strings, and the domain of my quantity is n. That's just the mathematical way of expressing the same. What is important is that with that second definition, this information about the domain, the enforcement of the domains, is separate from the definition. It's on top. It's extra information, right? So I have this definition that's called the schema, right? That I have these attributes and these domains. And then I can enforce or check if I take a relational table as a set of maps, and these maps have the same support, so they fulfill the constraint of relational integrity. I can ask the second question, do my maps also fulfill my domain integrity constraint? In other words, formally, what you ask is that if you have a tuple or a record or a row, whatever you call it, C, and if you have an attribute A that is associated with the domain D with my schema, so we ask for a specific domain, the question I am formally asking is T point A, so T point A would be the value in there, T point A, right? Is T point A in my domain D? That's the question I'm asking. For example, here, if this is an integer, is T point customer ID, which is 5, is it an integer? Right, because I asked that the security ID, oh, that's, yes, here, because security ID must be an integer, because that was customer ID, I think here. Yeah, customer ID, sorry. T.customer ID must be, T.customer ID must be an integer. So I basically ask the question, is T point A, the value here, is it in the domain that I want to enforce right there? If this is true for every single value in my table, every value is such that within the same column, all of the values belong to the domain specified here, then my data is valid against my schema. In other words, my relational table fulfills domain integrity. For whom is that clear? It's really just checking the types of the values. Okay, so this is what we check really. For example, first name must be a string. Are these all strings? Customer ID must be an integer. Are these all integers, right? These are counterexamples where domain integrity is not fulfilled. Customer ID must be an integer. This is not an integer, right? So this is a case where it's broken. All right. Now, so this was my second definition. A relational table is a set of maps, and I have these additional constraints. Relational integrity, all maps must have the same support. Domain integrity, the values in the same column must be in the domain of the column. All right. As a reminder, in the textbooks, the definition you will often find is not that second definition as a set of maps. You will often find the definition as a relation over domains with all the problems that we have discussed. So in textbooks, the way you do it is that you say, okay, this is my schema with my attributes and my domains, and then you define the data as a relation over the domains. If you do it in that way, you get for free relational integrity and domain integrity by definition. You get that for free in there. In the second definition, you have to add it on top, right, as additional constraints if you define as sets of maps. Okay, so we did a lot of math. Now we can actually describe our relational tables like this. As you can imagine, this is not how database people think. We will never actually in that lecture actually draw data like this. This is how we will draw data. This is so much more intuitive. And again, that's thousands of years old. Okay, this is how database people think. But at least now we have a strong mathematical formalism that tells us exactly what this is mathematically. It means that in subsequent lectures, we'll be able to define all kinds of algorithms and manipulation primitives to modify tables in a mathematically rigorous fashion. Okay, so now just repeating things to wrap up. So this here is an attribute, security ID, and these are all the values associated with these attributes. This is here a record, and now you understand why we also call it tuple or row or whatever. So we also call it tuple for historical reasons, because that's the first definition, where it's actually a mathematical tuple. This is called a relation or relational table also for historical reasons, because historically a relational table is defined as a relation. The order of the attributes in the relational model does not matter. In the second definition, it does not matter. In the first definition, you need to wave your hand a bit for it not to matter. Basically say, okay, a relation or relational table is a relation over domains, but the order of the attribute doesn't matter. And if you wave your hands enough, then you can convince yourself that you don't care. But mathematically, the order is still there, right? But in the second definition, the order of the attribute is irrelevant because these are maps. Okay. The order of records also does not matter. This is true in the two definitions. In the first definition, because a relation is a set of tuples, since it's a set, there's no order. In the second definition, it's a set of maps, but since it's a set of maps, the order doesn't matter. Why? Just because it's a set. In a set, there is no order, right? Okay, so in the life cycle of a database, I'm checking the time that I'm still on time. In the life cycle of a database, what happens is that when you create your data, you create a new table, you have to fill in some paperwork. The paperwork is the definition of the schema. So basically, you specify the schema of a table, you give it a name, you say, okay, we're going to have this attribute and this attribute and this attribute, university, city, and so on. The attributes are going to have this and that domain. This is going to be a string. This is going to be a natural integer. This is going to be a date. And this is stable. You do it once, typically. You do it once. And then you can start pouring data into your table. Thanks to a relational database management system, you have the absolute guarantee that the data you pour in there will respect relational integrity and domain integrity. It's a guarantee of the system. If you try to insert something that wouldn't validate against the domain, you would get an error. The system will not even let you do that, right? So this is stable, this is a schema, and typically the data there will evolve over time. Imagine you are a company. You have a table that is a list of customers or a list of products. As the days pass and your company is having its own life, customers will come, customers will go, you have no new products and so on. This will not change. The attributes and domains will not change, but the sets of maps will evolve. You will update data, you will delete tuples, you will add tuple and so on. So this is called a universe. So when a table evolves, the set of all the tables that respect the same schema is called a universe. Okay, now a little bit of sweeping in all corners from the math. You know, in linear algebra, you consider vector spaces. There is the case where the dimension of the vector space is 0, right? And whenever you have a proof, you need to check that it's also true for the corner cases, right? So let's go to the corner cases. The way we defined a relational table, it can be empty. A set of tuples could be empty, a set of maps could be empty. So in fact, if you have a table with just a schema and no data at all, it is a relational table. That's perfectly fine. It's just an empty table, right? You could also have a table that has just one record. That's also fine, right? That's absolutely fine. What you cannot have is duplicates in the attribute names. This is not allowed. Why? Because we said it's a set of attributes, right? In a map, you can only map at most one value with every string by definition of a map. The records must also be unique with the definition we gave. Why? Because it's a set of maps. It's a set of maps. In a set, you cannot have duplicates, right? It's also true as a set of tuples, right? In a set of tuples, you also cannot have duplicates. So records must be unique, okay? However, and this is also a benefit of the second definition, in the future, so the future of 1970, so now it's the past, but after having defined the relational model as sets of tuples, sets of maps, it was a very natural thing to do to say, why don't we relax things a bit? Why don't we allow bags of maps, meaning we allow for repetition? Why don't we allow lists of maps, meaning that the order of the records is important? And these would be flavors of the relational model. So there are three flavors of the relational model. There is the historical flavor as a set of maps. There is the bag of maps flavor where you can repeat records, but the order doesn't matter. And you have the list of maps where the order of the records actually matters. In modern implementations of relational database systems, these are actually the ones you will find. So the set of maps, I think, I'm not sure there's many systems today that would actually use sets. So most systems will allow you to have duplicates, and most systems will allow you to have lists. All right? So now, if we summarize things, when we define a relational table as a set of maps, we have additional constraints that we enforce. Relational integrity, meaning they all have the same support, they all have the same columns. Domain integrity, that's with our schema, that the values in the same columns must be in the same domain. The third one is called atomic integrity, and I'll explain what it is. This is the third one. Before I do, I'm going to repeat things. I love to repeat things. This is how you learn. If you keep repeating the same things, at some point, you remember it. So I'm repeating what relational integrity is. Relational integrity means we have a set of maps, all have the same support, and thus I can pass them into a table like this, right? This is a counterexample, right? This is messy. There's missing values. This is missing. This is an extra superfluous value. This is missing. In here, relational integrity is broken. This here is not a relational table. Okay, so that's relational integrity. That's a counterexample. Atomic integrity, that's the new one, the third. I called it number 2 because it's in a different order, but this is the third rule we learned today. Atomic integrity means that the values here are atomic. What does it mean to be atomic? Well, I'm going to show you what it does not mean. It's much easier that way. This is what it does not mean. We disallow to have tables in tables. It's like the Inception movie. Who saw the Inception movie? A dream in a dream in a dream in a dream. It's the same, a table in a table in a table in a table. You could have a table in a table, right? Because I didn't say anything about values. So the value could be a table. So you could have a table in a table in a table. But we disallow that traditionally in the relational model. And that means that we have atomic integrity. We just have atoms. This wouldn't be atomic because you have more structure in there. So here, atomic integrity is broken. And the third one, domain integrity, we already saw that one. This is where you have the domains here. And you specify this is a string, this is a string, this is a Boolean, this is an integer. Here, it's broken because 0 is not a Boolean, it's a number. And this here is not an integer, it's a string. Right? So you should clean that up. In fact, people spend millions of dollars cleaning things up. So you could turn the 0 into a false, and you could turn 31 into a 3 and a 1, or 1931, right? Okay, so now you have the definition as a set of maps, and you add on top domain integrity, tabular or relational integrity is just the same thing. I should have fixed it, and atomic integrity. So you have these three additional constraints on the set of maps. Okay, so now I'm going to check before you go that you followed what I have been telling you. So please just quickly answer this. This is my way of controlling my speed. So if I see that everybody understands everything, maybe I can accelerate a bit, go further into things. If I see that everybody is lost, then I can slow down or I can re-explain things. So I'm going to try regularly to ask you that and make sure that everybody is following and nobody is left behind. All right, display it. That's very good. So this is my goal. My goal is that most of you understood at least 80%. Probably not everything. It's never the case, right? Maybe you need to read again or look into things again. Maybe there's things that you need to maybe investigate a bit more. But this is my goal. If I see that many of you are below 80% or below 50%, then I will slow down. I will take the time maybe for an FAQ, let you ask questions. Some of you understood everything. That's really, really awesome. If everybody understands everything, I will just accelerate. Okay, so thank you very much for that. We are a bit ahead of time, so you'll be able to go to the Mensa early. I just want to summarize once more what we did today. A relational table is a set of maps, even though we saw that there's also flavors, a list of maps, bags of maps, different way of doing that. And we put 3 constraints on top. Relational integrity, all the maps must have the same support, the same columns. Domain integrity, the values in one column must all be in the domain of that column. And third, atomic integrity, we do not accept tables in tables in tables. Okay, so this is it for today. Enjoy your meal with hopefully no queue in the Mensa. And I'll see you next week for the continuation with a practical lecture. Thank you.